Chemical kinetics is the investigation of the rate at which chemical reactions occur and the factors that affect them. If you consider familiar reactions such as the explosion of a firecracker or the rusting of a ship, it is clear that chemical reactions occur at a wide variety of rates. We can determine reaction rates by observing either the disappearance of a reactant or the appearance of a product. To determine the rate, we must find a measurable property associated with the change in quantity of a reactant or product. What we end up measuring will determine the units that will represent reaction rate. For most reactions, the rate is greatest at the beginning of the reaction and decreases as a reaction proceeds. Because the rate changes as a reaction continues, reaction rates are generally expressed as averages over a particular time period. The average reaction rate is the change in a measurable quantity of a chemical species over the change in time. We generally report this as an absolute or positive value. The table shown below outlines several ways we might determine the rate of a reaction, although which ones we could use depend on the reaction. Additionally, reactions involving color changes could be analyzed using a spectrophotometer. Note the different units that correspond to each method. Also note that the concentrations of pure solids and liquids are constant and thus would not be used for the reaction rate. The same goes for the volume of liquid water, as water is often the solvent for reactions. The technique used to measure the change in the quantity of a reactant or product varies greatly depending on the reaction involved and the apparatus available. One piece of apparatus that can be used to measure the production of a gas in a closed system is a manometer. This device measures the partial pressure of the gas formed in a reaction. Gas production might also be measured using a pneumatic trough and a gas volume measuring tube called a eudiometer. If a gas is leaving an open system, there will be a change in mass that can be measured using a balance. Let's do an average rate calculation. A paraffin candle is placed in a petri dish on an electronic balance and combusted for a period of 15 minutes. The accompanying data is collected. First, we will calculate the average rate of combustion of the paraffin over the 15-minute period. We should begin by writing down the balanced chemical reaction. Hydrocarbon combustion always involves a reaction with oxygen to form carbon dioxide and water vapor. Note that the change in quantity being measured is the mass, all of which is lost due to the combusted paraffin being converted into the two gases. We get our rate by dividing the change in mass by the 15-minute time interval to give us an answer with units of grams per minute. Remember that the rate should be expressed as an absolute value. Next, we want to calculate the average rate of formation of water vapor for the same period. We need the mole ratio to convert from paraffin to water vapor, which we get from our balanced chemical equation. We begin with the reaction rate we just calculated and convert from grams of paraffin to moles of paraffin, to moles of water vapor, and finally to grams of water vapor to give us our answer. For part C, we assume that paraffin is combusted at the rate calculated in part A, and we want to calculate how long it will take to produce 4 liters of carbon dioxide gas at standard temperature and pressure. We want 1 unit for our final answer, so we will begin with a quantity with 1 unit and convert it. Knowing that there is 1 mole for every 22.4 liters of gas at STP conditions, we can use the mole ratio to convert to moles of paraffin. Since we have the rate of reaction in terms of the paraffin, we can then calculate the time required to produce 4 liters of carbon dioxide. The key in general to these kinds of problems, where derived units are involved, is to determine which form of the conversion factor to use and where to begin. Intuition tells us that in order for a reaction to occur, the reacting particles must contact each other, which means that anything resulting in an increased frequency of particle contact must make a reaction occur faster. 3 factors that can be manipulated to increase the frequency with which particles come together are surface area, concentration, and temperature. Additionally, the nature of the reactants affects reaction rate, and we can speed up the rate of reactions using a catalyst. When reactants are present in different states in a reacting system, we say that the reaction is heterogeneous. In these reactions, the reactants can only come into contact when they meet at the interface between 2 phases. Increasing the surface area of a solid will allow the reactants to come into contact more often, and thus increase the rate of a heterogeneous reaction. The rates of all reactions are affected by the concentrations of the dissolved or gaseous reactants. When more gas particles are placed in the same volume of a container, the partial pressure of the gas has increased. We can also decrease the volume of the container to increase the partial pressure. Increasing the concentration or partial pressure of a gas will increase the rate of a chemical reaction. Remember that the concentration of pure solids and liquids cannot be increased because the moles per liter will always remain constant. Recall the relationship between kinetic energy and temperature. An increase in temperature will not only lead to particles striking one another more frequently, but will also result in the particles striking one another with more energy. Increasing temperature will increase the rate of a reaction for two reasons: more frequent and more forceful collisions. Because of this, temperature is the most significant factor that affects reaction rate. Ionization energy, electronegativity, ionic and molecular polarity, size, and complexity of structure are factors that affect the breaking and forming of chemical bonds and hence chemical reactivity. One example is the formation of silver chloride precipitate. This occurs much faster than the formation of silver acetate precipitate because the complex structure of the acetate ion makes it more difficult to achieve the correct orientation to bond successfully. In general, at room temperature, the rate of aqueous reactants is greater than the rate of gaseous reactants, which is greater than the rate of liquid reactants, which is greater than the rate of solid reactants. Catalysts are substances that increase the rates of chemical reactions without being used up or altered. This means they are not included in chemical reactions, although sometimes a formula is shown above the arrow between the products and reactants. We will touch on catalysts again later on. An inhibitor is a species that reduces the rate of a chemical reaction by combining with a reactant to stop it from reacting in its usual way. Here we are given the equation for the combustion of paraffin and asked to list ways to increase the reaction rate. A good exercise would be to pause the video and to try to come up with some ideas before we go through the answers. This is a heterogeneous reaction, so we can consider surface area. We can increase the concentration or partial pressure of oxygen gas, raise the temperature, or add a catalyst. Increasing the partial pressure of carbon dioxide or water vapor will have no effect on the reaction rate because they are both products. The rate of a reaction is directly proportional to the product of the concentrations of the reactants. Shown below is an example of a relationship called a rate law. The proportionality constant, K, in this case is called a rate constant. Every reaction has its own unique rate law and its own unique rate constant. The values of the exponents, x and y, are called reactant orders. The higher the order of a particular reactant, the more a change in the concentration will affect the reaction rate. The overall order of the reaction is the sum of the reactant orders. When reacting particles collide with one another, each collision is unique in its energy and direction. Collision theory states that reaction rates depend upon the number of collisions per unit time and the fraction of these collisions that succeed in producing products. The large number of collisions in a reacting sample results in a wide range of velocities and kinetic energies. Only a small percentage of the molecules in a given sample have sufficient kinetic energy to react. The minimum kinetic energy that the reacting species must have in order to react is called the activation energy of the reaction. Reactions often occur in a series of steps called the reaction mechanism. The activation energy of a reaction often reflects the difference between energies required to break bonds and energy released during bond formation during the early steps of the reaction mechanism. The only way to change the activation energy of a reaction is to change its reaction mechanism. This is exactly what happens when a reaction is catalyzed. This is a kinetic energy distribution diagram for a sample of matter at two different temperatures. It also shows two different activation energies, where the second activation energy represents the activation energy without a catalyst, and the first activation energy represents a lowered activation energy that results with a catalyst present. In both cases, the shaded area under the curve represents the number of particles capable of colliding effectively, and this increases at higher temperatures. There is still one more factor that complicates collision theory even more. Collisions possessing the activation energy don't always result in reaction, because to be successful, the molecules must be oriented properly towards one another. An example of this is carbon monoxide and nitrogen dioxide reacting to form carbon dioxide and nitrogen monoxide. In addition to attaining the activation energy, the geometric shape and the collision geometry of reacting particles must also be favorable for a successful collision to occur. Relating collision theory back to our discussion about the factors affecting reaction rate, we can see that increased temperature, concentration, and surface area all increase the frequency of collisions, leading to an increase in reaction rate. The presence of a catalyst and increased temperature both increase the fraction of collisions that are successful. The initial rate is the instantaneous rate determined at the very beginning of a reaction. The slope of a tangent line drawn to the curve at the beginning of a reaction is greater than that of any other tangent. The initial rate of a reaction depends on the concentration of the reactants present, as predicted by collision theory. The data from a series of trials can be summarized in a table such as this. First, we will use the data in the table to determine the rate law. There are two different ways we can go about doing this. We should start by writing down the form of the rate law and putting in x and y for the exponents. Now we need to find what the exponents are. First, let's find the value of x. We will use the data from trial 1 and trial 2 because the concentration of reactant A is varied while the concentration of reactant B is held constant. We can demonstrate the relationship between the change in concentrations and the change in rate mathematically by setting up a ratio of the rate laws for the two trials like this. We make the correct cancellations and are left with 2 to the power of x is equal to 4. This means that x is equal to 2. Now we can find y. We will use trial 1 and trial 3 because only the concentration of B is varied. We carry out the same process as before and see that y is equal to 0. We can then substitute our exponents into the rate law to get our answer. The rate is proportional to the square of the concentration of A. We could also have found the reactant orders using a slightly different method. We see directly from the table that as the concentration of A is doubled, the rate increases by a factor of 4. This means 2 to the power of x equals 4, so x equals 2. Going from trial 2 to 3, we see that A is decreased by a factor of 1/2, B is increased by a factor of 2, and the rate decreases by a factor of 4. We write down an equation to solve for y. X is equal to 2, so y must be 0. The rate law can be written down as before. Note that rate 1 and 3 could also have been used to solve for y. Now that the rate law is known, the values from one of the trials can be substituted into it to solve for the rate constant. This is a second order reaction, and the rate constant has units of liters per mole per second. An integrated rate law expresses the concentration of a species directly as a function of time. For a differential rate expression, calculus allows us to calculate a corresponding integrated rate law. A discussion of the derivation of 3 important integrated rate equations in chemistry is covered in the textbook. We will not cover the derivation in this video and simply summarize what the equations are. Let's take a look at the first order reaction. The rate is proportional to a reactant concentration to the power of 1. For the first order integrated rate equation, we have the natural log of the concentration is equal to the negative of the rate constant multiplied by time plus the natural log of the initial concentration. The half-life of reaction is the time it takes for 1/2 of a reactant to be consumed in a chemical reaction. For a first order reaction, the half-life is a constant value, the natural log of 2 divided by the rate constant. The half-life expressions can be derived by substituting 1/2 of the initial concentration in for the concentration and solving for the time. The unit for a first-order reaction rate constant is seconds to the -1. The rate of a second-order reaction, such as the decomposition of nitrogen dioxide, depends on the reactant concentration to the power of 2. Note that this time in the integrated rate equation there is no negative sign before the rate constant. The half-life is not constant for a second-order reaction, as it depends on the initial concentration. The smaller the initial concentration, the longer the half-life. Here, each successive half-life is double the length of the previous one. The units of the rate constant are liters per mole per second. The rate of a zero-order reaction does not depend on any concentrations and is thus constant throughout the reaction. The integrated rate equation does include a negative sign, just like the first-order one. The half-life depends on the initial concentration. This time, each successive half-life is half the length of the previous one. The units for a zero-order reaction are moles per liter per second. For all 3 of these reactions, the half-life is inversely proportional to the rate constant. The larger the rate constant, the shorter the half-life, which makes sense because a larger rate constant means the reaction will go faster. Now we will try out some calculations related to these concepts and equations. Here we are analyzing a first-order reaction. If the initial concentration of dinitrogen pentoxide is 0.5 moles per liter, how long will it take for the concentration to drop to 0.05 moles per liter? Well, seeing as we have a value for the initial concentration, rate constant, and final concentration, we can use our integrated rate equation for first-order reactions, rearranging and plugging in the values we solve for the time. Next, we are given an initial concentration of 0.25 moles per liter and need to find the concentration after 2 hours. Once again, we use our integrated rate equation to solve. To get rid of the natural log, we take e to the power of both sides. The concentration will be equal to e to the power of negative 5.68, which ends up being 0.0028 moles per liter. The decomposition of nitrosyl chloride occurs by second-order reaction kinetics with a rate constant K equals 0.020 liters per mole per second. We are asked to find the concentration remaining after 40 hours if the initial concentration is 0.45 moles per liter. To begin, we write down our integrated rate equation for second-order reactions. We are given values for the rate constant, the time, and the initial concentration, which we can use to find the concentration remaining. Plugging these values in, we can take the reciprocal of each side to give us an answer of 3.5 times 10 to the negative 4 moles per liter. A zero-order reaction has a rate constant K equals 0.025 moles per liter per second for the disappearance of reactant A. What is the half-life of this reaction if the initial concentration is 0.80 moles per liter? We begin by writing down the half-life equation for a zero-order reaction. If we forgot this equation, we could rederive it by using the integrated rate equation for a zero-order reaction and solving for the time when the concentration is half the initial concentration. We have all the values we need and we get an answer for the half-life. Next, we need to find the concentration of A after 15 seconds. Plugging the values given into the integrated rate equation for a zero-order reaction gives an answer of 0.43 moles per liter. This final question asks us to find the half-life of a first-order reaction with rate constant 0.0036 minutes to the minus 1. Notice how we do not need the initial concentration since the half-life for a first-order reaction is independent of the initial concentration. The half-life is equal to the natural log of 2 divided by the rate constant. In a first-order reaction, a plot of concentration versus time looks like the graph farthest to the left. The tangent line is steepest at the beginning of the reaction when the rate is the greatest. Plotting the natural log of the concentration versus time gives a straight line with a negative slope. The absolute value of the slope is equal to the rate constant. This matches up with our integrated rate equation for first-order reactions. The y-intercept is equal to the natural log of the initial concentration. The reciprocal of concentration versus time gives a parabolic shape with an upward curve. This is a graph of the concentration of hydrogen peroxide versus time for the decomposition of hydrogen peroxide. The concentration drops to 1/2 of its previous concentration every 654 minutes. This makes sense looking at our half-life equation. The half-life is a constant value and does not depend on the concentration of the reactant. For a second-order reaction, a plot of concentration versus time produces a curve similar to that of a plot of concentration versus time for a first-order reaction. The natural log of the concentration versus time plot of a second-order reaction produces a graph that is slightly less curved than the concentration versus time plot. A plot of the reciprocal of concentration versus time for second-order reactions gives a straight line with a positive slope. This slope is equal to the rate constant. This graph shows a concentration versus time for a second-order reaction. The half-life is inversely proportional to the rate constant. We can see that a larger rate constant results in a faster reaction and shorter half-lives. The relationship between concentration and time for a zero-order reaction is simply a straight line graph with a negative slope. The absolute value of this slope is equal to the rate constant for the reaction. The natural log of the concentration versus time relationship is a convex curve, and the reciprocal of concentration versus time plot is a concave curve. This graph shows how halving the initial reactant concentration for a zero-order reaction halves the half-life. However, the slope remains the same for both plots as it is equal to the negative of the rate constant. Let's try a graphical analysis problem. We first need to complete the table, which is pretty straightforward. We then use this data to make 3 plots to determine if the reaction is 0, first, or second order. When the data is plotted, the graphs look like this. Clearly, the reciprocal of concentration versus time graph is the only linear one, so the reaction must be second order with respect to nitrosyl bromide. Once the rate law is written, the slope of the reciprocal of concentration versus time graph can be calculated. This is equal to the rate constant. Enthalpy is potential energy that may be evolved or absorbed as heat. A general change in enthalpy is symbolized as delta H. There are two ways to express the delta H value associated with a chemical reaction. Delta H notation is when the energy change is written after the equation following a delta H equals symbol. A thermochemical equation includes the energy change as an integral part of the chemical equation. To investigate why the enthalpy stored in reactants differs from that in the products, we need to look at bond energy. The electrons in the atoms of molecules have potential energy by virtue of their position relative to the positive nucleus. This chemical potential energy is called bond energy. We know intuitively that breaking something requires energy. Bond breaking requires energy input while bond forming results in an energy release. In an endothermic reaction, the energy absorbed to break bonds is greater than the energy released during bond formation. These reactions have positive delta H values. In an exothermic reaction, more energy is released during bond formation than is absorbed during bond breaking. These reactions have negative delta H values. When reacting molecules come together and have favorable collision geometry and kinetic energy at least equal to the activation energy, they interact to form a high-energy, unstable, transitory configuration of atoms called an activated complex. The activated complex is formed when potential energy is at a maximum and kinetic energy is minimized. This graphical representation of the energy changes taking place during a chemical reaction is called a potential energy diagram. The vertical axis measures potential energy in kilojoules per mole. The horizontal axis is sometimes called the reaction coordinate or the progress of reaction. The activation energy is the difference between the potential energy of the activated complex and the total potential energy of the separated reactant molecules. The enthalpy change is the difference between the total potential energy of the products and the total potential energy of the reactants. This is independent of the activation energy. In this case, the potential energy of the products is less than that of the reactants, so the reaction is exothermic and energy was released. Changes to concentration, surface area, or temperature will affect the rate of a chemical reaction, but they will not affect the appearance of a potential energy diagram. Under certain conditions, many chemical reactions are reversible. The potential energy diagrams for a forward and reverse reaction are mirror images of one another. Delta H for the forward and reverse reactions will have the same magnitude and opposite signs. The activation energy is always smaller for the exothermic reaction, as we can see from these graphs. Recall that one way to increase reaction rate is using a catalyst. This is because catalysts provide an additional reaction mechanism with a lower activation energy. The catalyst is neither consumed nor changed following the reaction. They must be consumed in one step of a reaction mechanism and be regenerated in a later step. Catalysts reduce the activation energy to the same extent for both the forward and reverse reaction in a reversible reaction, so both forward and reverse reaction rates are increased by the same amount. A consequence of the fact that catalysts are consumed and regenerated is that more than one activated complex is formed, which we can see on this potential energy profile for a catalyzed reaction. The activation energy is simply the difference in the potential energy of the highest energy activated complex and the reactants. In this example, we need to use the provided potential energy diagram to answer several questions. It might be a good idea to try to answer these questions before watching the rest of the video. Is the reaction endothermic or exothermic? Well, we can see that the products have more potential energy than the reactants, so energy had to be absorbed. This means the reaction is endothermic. Next, we have to identify the meanings of each of the measured values on the diagram. We will proceed from left to right. The first arrow shows the difference between the potential energy of the activated complex for the catalyzed reaction and the potential energy of the products for the forward reaction. But the products for the forward reaction are the same as the reactants for the reverse reaction. So this arrow shows the reverse catalyzed activation energy. The next arrow is the difference between the potential energy of the activated complex of the uncatalyzed reaction and the potential energy of the products, meaning it represents the reverse uncatalyzed activation energy. This arrow is for the forward catalyzed activation energy. The following arrow shows the difference between the potential energy of the uncatalyzed activated complex and the catalyzed activated complex. Next, we have the potential energy of the uncatalyzed activated complex. The difference between the potential energy of reactants and products is the enthalpy change, or delta H. The final arrow is for the activation energy of the uncatalyzed forward reaction. What is delta H for the uncatalyzed forward and reverse reactions? To get delta H for the forward reaction, we subtract the potential energy of the reactants from the products. We get 40 minus 20, which gives us positive 20 kilojoules per mole. To get the delta H for the reverse reaction, we take the potential energy of the products and subtract the potential energy of the reactants. Be careful, the reactants and products of the reverse reaction are the opposite of the forward reaction. We get the negative of our delta H value for the forward reaction, which is what we should be expecting here. The question also asks about delta H for the catalyzed reaction. However, the answers would just be the same as above, as catalysts do not affect the potential energy of reactants or products. Now we must find the activation energy for the forward and reverse uncatalyzed reactions. To determine this for the forward reaction, we subtract the potential energy of the reactants from the potential energy of the uncatalyzed activated complex. For the reverse reaction, we do this as well, remembering that the reactants and products are swapped for the forward and reverse reactions. What about the activation energy for the catalyzed reactions? This time we will not get the same answers because catalysts cause a new, lower energy activated complex to form. We will use this activated complex's potential energy in our calculations, and otherwise carry them out the same as was done previously. A reaction mechanism is a series of steps that may be added together to give an overall chemical reaction. The individual steps in such a series are called elementary processes, which are themselves individual balanced chemical reactions. The molecularity of each elementary process is defined as the number of reactant species that must collide to produce the reaction indicated by that step. A reaction involving one molecule only is called a unimolecular step. One involving two species is a bimolecular step, while one involving three species is a termolecular step. Termolecular steps are rare as they require the simultaneous collision of three molecules in correct orientation. The first collision or decomposition of a reactant in any multi-step reaction mechanism always produces some product that is consumed in a later step of the mechanism. This species is known as an intermediate. As we have seen before, a catalyst is consumed in one step and regenerated in a subsequent or later step. Catalysts in biological systems are referred to as enzymes, which are proteins that have an active site. We can classify catalysts as one of two categories. Heterogeneous catalysts are those in which reactions are limited to their surface area only. Most of these catalysts are solids, such as the transition metals platinum and nickel. One example of a heterogeneous reaction is the addition reaction involving ethene and hydrogen. First, molecules of ethene and hydrogen approach and absorb to a metal surface. The hydrogen-hydrogen bond is broken, and one of the hydrogens bonds to the ethene. Another carbon-hydrogen bond forms and ethane is released. Heterogeneous catalysts are also found in catalytic converters in our automobiles, which transform harmful pollutants such as carbon monoxide and nitrogen oxides into carbon dioxide, water, and nitrogen gas. The other type of catalysts are homogeneous catalysts. These exist in the same phase as the rest of the reaction system. An overall reaction cannot exceed the rate of the slowest elementary process. The slowest elementary process in a reaction mechanism determines the overall reaction rate and is known as the rate-determining step. Reasons that can cause a step to limit the overall reaction rate include the step having complex collision geometry, a high activation energy, low concentrations of reactants, or a termolecular collision. Additionally, each step has its own rate constant and its own activation energy, because they involve different chemical species and potential energies. The potential energy diagram for a particular reaction will have the same number of peaks as there are steps in the reaction mechanism. Here is an example of a potential energy diagram for an uncatalyzed reaction. A methanoic acid molecule is energized, forms an activated complex, and decomposes into water and carbon dioxide. This happens in a single step. When a catalyst is added, there are now 3 peaks which correspond to 3 different steps in the catalyzed reaction mechanism. The second peak is the rate-determining step. To calculate the activation energy for the whole process, we subtract the potential energy of the reactants from the potential energy of the highest energy activated complex. For a reaction mechanism to be valid for a particular chemical reaction, it must fit these criteria. The elementary steps must algebraically sum to the overall balanced equation. Each elementary step is most commonly unimolecular or bimolecular. There is an extremely low chance of more than 2 particles colliding at once with sufficient energy and proper geometry. Finally, the reaction mechanism must correlate with the rate law. The deduction of a rate law from a reaction mechanism involves 4 main steps. We begin by locating the rate-determining step, which will be the slowest one. A temporary rate law expression can then be written down. Next, we will likely have to write down an equilibrium expression using one of the other steps, and then use the expression to substitute for appropriate species in the temporary rate law. Note that intermediates should not appear in the rate law. The rate law should only contain reactant species and, in rare cases, a catalyst. Let's put these methods into practice and deduce a rate law from a mechanism. We are provided with the following mechanism. First, we are to determine the overall reaction. We can cancel species appearing on both sides of the arrows. Then we sum the remaining species to get the overall equation. Hypochlorous acid, hydroxide, and hypoiodous acid are all generated and then consumed, so they are intermediates. Water is consumed and then regenerated, so it is a catalyst. To find the rate law, start by locating the rate-determining step. In this case, it is directly given to us. It is the second step. This step can be used to write a temporary rate law. Remember that the rate is dependent on the reactants and not the products. The rate constant is temporary as well, so we write it down as K prime. The equilibrium or fast-forward reversible step can be used to come up with another expression. As hypochlorous acid is an intermediate, we do not want it in the rate law. We rearrange our second expression and substitute it in for the concentration of hypochlorous acid in our rate law. Now we can write down the rate law. The product of K prime and the equilibrium constant is equal to the overall rate constant K. Because this redox reaction is occurring in a basic solution, it is okay for the concentration of hydroxide to appear in the rate law expression.